Let's move on to the characteristic function approach. Recall still all of the previous assumptions in your mind. They are no longer on the board, but you still have them in your mind. Stuff such as the claim number process n is an inhomogeneous Poisson process. So we know for a fact that the increment from time 0 to t minus s has the same distribution as the increment from time s to t, because it's homogeneous in our assumption. So Cramér-Lundberg model. And also other things, such as the xi are IID, also by the Cramér-Lundberg model, and that the xi and the n's are independent. Okay, so those were the assumptions, and let's just get started. So first of all, I think it's probably easiest to start off by looking at this expression here. So the characteristic function for s of t minus s. And probably the easiest way to do that is just first calculate for s of t, because then we can just plug in the value t minus s afterwards. It's mostly just because then I don't need to write as much. So let's try to look at the mean value of e to the I x. So I'll just write for x greater than 0. We will calculate this. S of t. So where do we start? Well, we can start by putting in the definition of the total claim amount. So the definition of the total claim amount is the sum of the first claims x1 and so on up until the number of claims we have at time t. And then it's like, well, we have an n up here. What should we do with it? What should we do with it? We don't know what to do else. So what else to do? Then use the double expectation property. So double expectation property. And the double expectation property is just one of those typical conditional expectation things where the mean value of a conditional expectation is just equal to the mean value of this variable inside itself. I mean, it is, if you use the abstract definition of a conditional expectation, this is actually the definition of a conditional expectation. And if you go the more intuitive, discrete case route, then you can also convince yourself that this is the case. Okay, so let's see, what do we have? The exponential of Ix, and then the sum of xi's from 1 up to n of t, and in the exponential and a condition on n of t. Okay, so here a condition on n of t. What do I do now? Well, one thing that we can try to do, since we're still kind of working on this stuff quite in basic terms, is that we can try to calculate this mean value here, because the mean value of this thing inside, well, it's quite easy to calculate. We just look at which different values can n of t obtain. And n of t is Poisson distributed, so it can be 0, 1, 2, 3, and so on, and multiply each of the cases with the probability that it will attain that value. So let's see. I have the sum for k going from 0 to infinity, and then I have the different cases here, the conditional expectation of the exponential I(x) sum of the first n of t xi's, I equals 1 to n of t, and given that n of t is equal to k. So then I multiply by the probability that that will occur. So just typical conditional expectation, blah, blah. What do we then do? Well, we have to try to tackle this thing. You know, we have to try and figure out what is it? What is it? I think I forgot a parenthesis here. So just recall that what we have from insurance and law, the mean value of x given some event. So this is an event. Okay, so there's a difference here between up here where I condition on a stochastic variable and down here where I condition on an event. When I condition on an event, I can actually find a concrete number that this thing evaluates to. When I condition on a stochastic variable, this conditional expectation is itself a stochastic variable, because according to which value the stochastic variable attains, the conditional expectation will attain different values. So the conditional expectation of something conditioned on an event is defined as 1 divided by the probability of that event multiplied by the mean value of that something, some stochastic variable, restricted to the event. Yes, so this is a good old insurance and law curriculum. So let us try to write that up here. So this thing, here I condition on the event that n of t is equal to k. So it evaluates to 1 over the probability that n of t is equal to k, multiplied by the mean value of the exponential of I(x) sum up to n of t xi. As such, restricted to the event that n of t is equal to k. Yes, so restricted to whatever I condition on, like this. And then I also have the last part, the probability that n of t is equal to k, and because I'm kind of lazy, I'll just write it up here. Okay. So, what do we have now? Well, we do certainly have that some things cancel. These two things, they cancel, right? And then I have that, I have a sum from k equals 0 to infinity, and I have something in here. So, what do I have in here? Well, first of all, let us just notice one thing, and that is essentially what I write here is that n of t is equal to k. And that means when I calculate this mean value, then it will be based on the fact that n of t cannot be anything else than k, which means that I can plug in the value of k in the top of my sum. So up until now, nothing really exceptional has happened because, to be honest, I have used none of the conditions that I have from the Cramér-Lundberg assumptions. So nothing interesting has happened yet. But now something interesting will happen because in the Cramér-Lundberg assumptions, we assume that the xi and the n's are all independent. And because of that, so the x and the n process, they're independent, and because of that, I can move this indicator, the mean of this product, I can split it up into the mean of two products. So I will have the mean of one of the indicator that n of t is equal to k, multiplied by the mean that, multiplied by the mean of this thing here. And what's nice about this? Well, the thing that's nice about it is that now I have removed the n of t from the top of the sum. And that's really comfortable because what I can do now, well, I can do two things. The first thing I can do is I can notice that this here, the mean of an indicator is just the probability of the event that the indicator indicates. So this is just the probability that n of t is equal to k. And over here, what I can use now is the xi are independent, right? So xi are independent. So xi is independent from xj for all I and j that are different. And oh, this is not nice. I should write j here maybe because we're using the i's with the complex calculation stuff. So with the complex numbers, I'll remember that in the future. Okay, so what I can do now is I can just say, well, this sum, it goes outside as the product. So it is the product of the mean of the exponential of I x xj, or just x1 because they're IID. So I can take that to its own power k times. And actually, if I'm really interested in just finishing this off, I can also write up a closed expression for it. So let's just do that since we're almost there anyways. So what do I have? I have probability that n of t is equal to k. So let's just recall that n of t is Poisson distributed with intensity lambda, and that means that it has point probability in k given by e to the minus lambda, lambda to the k divided by k factorial. And afterwards we have this thing here, which is just itself, but I mean this is also taken to the kth power, right? Oh, sorry, it's lambda t here. What? Let's just erase this. So n of t is Poisson distributed. I should write that down in a bubble. N of t is Poisson distributed with parameter lambda t because n has intensity lambda. That means that this point probability is given as e to the minus lambda t, then lambda t to the k divided by k factorial. But over here we also have something to the k. And basically what we see now is I have e to the minus lambda t outside, and then I have the sum over k's for lambda t multiplied by this thing to the k divided by k factorial. And we recognize the Taylor series for an exponential expression, since we know from numerical analysis, if you guys can remember that. I know it's a long time ago, but and we also know this from analysis 1, I think, that this series here is equal to e to the x. So just write this in your notes because it's good to have. We'll be using it quite a lot. So this is equal to e to the minus lambda t multiplied by e to the lambda t mean of exp I x x1 to the k. Okay, and this then can be changed a little bit. I mean, now we're just doing stuff for fun. So minus the t multiplied by 1 minus mean. This. So essentially, the characteristic function in the case that we're looking at here, it can be expressed using the characteristic function of the crane sizes. And that was finding the characteristic function of n of t, of s of t, and we were interested in it for s of t minus 1. So hence, the characteristic function for s of t minus, did I say 1? I meant s. T minus s is equal to e to the minus lambda t minus s multiplied by 1 minus the mean value exp I x x1 to the k. And now we're here, that's good. And in the next video, we will try to show that the characteristic function for the increment in total claim amount from time s to t is also given by this exact expression. And when we have done that, we are done with exercise 5a.